Hi, I'm Ben-Yaakov. This presentation is entitled The Controlled Inductor and an LLC Converter Application Example. I'd like to thank Vladimir and Michael for the design construction of the variable inductor and for taking the laboratory measurements that will be presented in this video. Both of them are with the Hulda Transformers company in Israel. Let me start off with some history. In 1994, I, in collaboration with, at that time, master student Dror Medini, and now Dr. Medini, we published a paper entitled The Current Control Variable Inductor for High Frequency Resonant Power Circuit. The structure of this inductor looks like that, shown here in a configuration of two E-cores clamped together with a gap here. We have a center leg, which is actually an AC inductor, a power inductor, because there is a gap here, so it can store energy. And then on the left and right legs, we have windings. Actually, they are continuous here, and this is for DC biasing. The objective here is to change the inductance that is seen here by injecting a current into these DC terminals. The operation of this variable inductor can be explained by this simple illustration. Without DC, we have a regular inductor. Then with DC, we are pushing this ferrite part towards saturation, so therefore the permeability of this area here is becoming smaller and smaller, and consequently the inductance that you see here now will be becoming smaller. So by injecting the DC, you change the permeability of this outer loop here, and therefore changing the inductance of the inductor. Now, since its invention, the controlled inductor was applied in many applications that were reported in extremely large number of papers. For example, a 2019 paper entitled A Comprehensive Analysis and Design of LLC Resonant Converter with Magnetic Control shows exactly the same construction as we have presented 25 years ago. Unfortunately, not all the papers gave credit to the original publication, but I guess this is part of life. So the variable inductors are really shown to be useful in resonant converters, PWM converters, LED driver, active power factor correction, and many others. In this presentation, I'm going to concentrate on one example, and that is the application of the variable inductor in the LLC resonant converter. Now the question is, why would you like to have a variable inductor in an LLC converter? Well, there are a number of reasons for that. First of all, by that you can actually operate the LLC with a fixed frequency. That is, rather than changing the frequency, you can change the inductance, and therefore you can fix the frequency at one given point. This could be very useful in cases in which it's not desirable to have a variable frequency, since the EMI is actually spread all over the place. It's moving from one point to another. It's very difficult to filter out. So in some application, there is a requirement that all switching will be done at a given frequency, and usually it is locked to a master frequency. So in this case, we can now run an LLC converter with a fixed frequency. There are other reasons, and that is that we can get a wider operational range, we can improve soft switching, and also we can improve the efficiency, as a matter of fact. So the idea behind this variable inductor is as follows. We have an inductor built around this double E-core with a gap. Now the flux of the AC is passing through here and here, while we have then a DC winding here and here. It's a continuous winding, but it goes in this direction, so therefore there is no interaction between the AC and the DC windings, and furthermore, by having two windings and the polarity of the imposed AC is as shown here, they are actually being subtracted. So as you look here at the DC bias terminal, ideally you will not see any AC. Of course, due to some mismatch you can have some, but most of the AC is subtracted. So on the one hand, we have a inductor, a power inductor that will be operated at some high frequency, and then we have this path here. Now this path here is all ferrite. There is no gap here. So by having a bias here, we are moving on the BH curve like that. The permeability, which is the slope here, is changing, and therefore we are changing the permeability of this outer rim, as I've shown earlier. And consequently, as you go up here, the inductance seen here at these two terminals will go down and down. Now it is very important that in this variable inductor, there is no gap in the DC path, or the flux of the DC, and with a gap, we are going to have a BH curve that will look something like that, and therefore in order to get to the area in which the permeability drops, you'll have to have a high H, meaning a very high current. So this is the idea here, that on one hand, the inductor is built around a gapped ferrite, while the DC sees only ferrite path without any gap. Now you can describe this structure, which you might call it integrated magnetics, by this reluctance model. Now if you are unfamiliar with magnetic circuits, there is a video in my YouTube channel which describes this whole issue of magnetic circuit, reluctances, etc., with an example, and I highly recommend that you watch it. So in this case, we have this reluctance represent the left side, this one the right side, and here it's the mid lag. Here we have only the ferrite at the beginning, and then it's going to change. And then we have here the ferrite, this is the part here, and the gap here, this is the gap. The definition of reluctance is 1 over mu A is the cross-section area, and L is the length of the section that you are describing, okay? So this will be, R1 will be this length here, and R4 will be this length here, and this will be divided between the ferrite and the gap. This is the ferrite length here, this and this is the gap. Now the voltage source here represent MMF, magnetic motive force, and this is N times I. Now I'm assuming a current of 1 amp, so this is why this is only N, and N will be just a number that I can change in the simulation. This will be simulated by LT-SPICE. Now the idea is then that as you inject here DC, you move up the BH curve of the ferrite around here, and consequently the relative permeability of the ferrite is changing, and therefore the total reluctance that you see from here through here and here is changing, and therefore the inductance you will see here will change. We'll see it in a minute. Since I'm going to do some simulation, I need some dimension here, some numbers. So I'm assuming a core of 5 by 5 and with a cross-section area of 1 centimeter square. The initial permeability of the ferrite is assumed to be 2000, and this is again the definition of the reluctance. And the permeability of the gap is of course like air or vacuum, and this is the number here. So here is an LT-SPICE representation of this structure. We have seen this before. This is the reluctances of the sections here. This is the MMF coming here, assuming 1 amp injection. And I'm also calculating on the run the inductance that will be seen here. And by definition, inductance is N times phi over I. Now in this reluctance model or magnetic model or magnetic circuit model, flux is represented by a current. So by taking the ratio of the current here, which is phi, multiplying it by the number of turns, dividing it by I, and since I is 1 amp, then therefore this expression is actually the definition of the inductance that would be seen here. So I can run this stepping the constant here, or the coefficient here, over a range, and this coefficient is changing the reluctance here and here to represent a change in the permeability. That is, for kV equal to 1, this constant equal to 1, this is the original permeability, 2000, and when it is, say, 10, then the permeability is 10 times lower, because I'm multiplying it and the permeability is in the denominator. So therefore, by stepping this kV, I can sort of mimic the situation in which the DC injected into the windings here of the outer legs, and the permeability is changing. And here is the result. We see here the inductance as a function of this change. So this is a change in the permeability, as I've said, like here, the original permeability here is 2000, and here it's like 200, and this is 20, and then it goes down even lower. And we see the inductance going from the nominal value of 33, or the maximum value of 33 about, and then it goes down. And this is with the initial permeability of 2000 with the structure that I've shown. This is of course just an example, and there are many other options to build this variable inductor. So let's move now to the resonant LLC converter. In the normal operation, we change the frequency in order to change the voltage ratio between the input and output. This is the normal operation. Here, we want to fix the frequency and change the inductance so as to change the input to output ratio. The normal operation, we're changing the frequency and thereby changing the voltage gain. These are curves for different Q, which is related to the RAC and the series inductance of the LLC converter. Now we are going to change the series inductance. Now the transfer function between output and input for the general case is this function. Fx is the ratio between the switching frequency and the resonant frequency. But the resonant frequency is a function of L sub r. Also, there is a factor here between the inductances and has here the L sub r, and also the Q here, this Q also has some L sub r. So obviously, when you are changing L sub r while keeping the switching frequency constant, you will change the output to input ratio. Of course, we can have an expression here to show it, but we rather do some simulation to illustrate it in a simple way. So here is the circuit for simulation, and I'm using here the so-called first harmonic approximation. And if you are unfamiliar, I have in my YouTube channel a number of videos related to LLC in which this is explained. And in this case, we have this series inductor, resonant capacitor, parallel inductor, and this actually represents the load. Now we're going to change this inductance. And there is a nominal value of 15, which I'm multiplying by some factor k, and I'm going to change this k by a factor between 0.5 to 3 with steps of 0.5. So this actually mimics the situation in which I am changing the L sub r in a resonant converter, in the LLC resonant converter. Mind you, this is an approximation, the first harmonic approximation. In a time domain model will give us better result, but just for the sake of simplifying things here in the explanation, I'm using this first harmonic approximation. And here are the results. I'm showing here two things. First of all, I'm showing the output to input ratio with the inductance of the series inductor as a parameter. So it's changing between 7.5 microhenry to 45 microhenry. And this is the gain that you'll get. This is gain here. And of course, we are going to work at one frequency, say one here. It'll be a fixed frequency. And by changing the inductance of the series inductor, we can change, as you can see very nicely, the gain. And then I'm showing here the input current, and this is this current here. And of importance is the phase of the current. We'd like the phase to be lagging in order to get zero voltage switching. And you can see that from here, we get the current lagging. So therefore, any point here, any frequency here can be fixed, and then we can change the inductance in order to control the gain. In order to illustrate the operation of the variable inductor in the LLC converter, we have taken an evaluation module by Infineon. It's a 600 watt LLC half bridge with a 12 volt output. So it's about 50 amp nominal current, or maximum current I should say. And what we did, we replaced the fixed series inductor, which is this one here, was replaced by the variable inductor. Here is the schematics of this module, this part, the power part. This is the transformer. The magnetization inductance of the primary is the LM, is the parallel inductor. And here is the series inductor, which is a discrete unit, which we have taken out and replaced by the variable inductor. And here are the results. You see that, first of all, we have changed the input from 420 to 350. The frequency was fixed while we have changed the input voltage and also the load between 470 in this case to 24. Okay? Now, this was done manually. That is, a change was made, like in the input voltage. The controller was running in closed loop, and obviously the frequency was changed in order to accommodate the change in, say, the input voltage. And then we adjusted the series inductor, or the inductance of the series inductor, such that the frequency will come back to 110 kilohertz. So this sort of emulates an operation with a fixed frequency. And here we see the change in the inductance between 50 and 13 microhenry. It's much less that I've shown earlier. No need for such a large change. And we see that by changing the inductance, we can accommodate all these changes. The current that is needed in this particular embodiment is about up to, say, 3.5 to 4 amp. Now remember that this current goes to a DC winding, which has, of course, resistance of just copper and very, very low voltage, because our DC of the copper will be low, depending, of course, the cross-section of the wire that we are choosing. In any event, this will encounter low power dissipation. Now, based on this result, one can clearly see that the variable inductor can, of course, run the LLC converter at fixed frequency. Now, obviously, there are many options here, many variables that can be adjusted, many optimization that can be done, but this is beyond the scope of this presentation. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps you would like to try it yourself and see whether you can implement the variable inductor in one of the applications that you are working on. Thank you very much.